So in this video, we're going to look at a variation on a theme. We've titled this KSP for solubility product, but we're really going to look at something that is probably better written as KEQ, or well, specifically K sub W. We're going to look at the equilibrium constant of water, but we'll see how it folds back to a KSP-like theme. So for the case of water, if we have pure water, and it disassociates to form hydrogen ion in aqueous solution plus hydroxyl ion also in aqueous solution. That is an OH minus there. We can ask, how far will this reaction go? How far to the right will this thing go? How much hydrogen ion and hydroxyl ion will we get out of any given amount of H2O? And notice this, 1 mole of water will give us 1 mole of hydrogen and 1 mole of hydroxyl. So since we're getting equal moles of hydrogen and hydroxyl, if we know the concentration of this, then we know the concentration of that. These will be the same. We can write the equilibrium constant, and we'll write it K sub W as the concentration of the products, hydrogen ion multiplied by hydroxyl ion, and then divided by the concentration of water. Well, if we have the concentration of water in water, and if this is pretty close to a pure system, let's just say it's pure water that's disassociating, then if this constant is very small, then essentially this is 100% or 1, and so this devolves into simply the products, hydrogen and hydroxyl ion, their respective concentrations. And so notice that with the reactants dropping out because they're equal to 1, we get something that looks kind of like a solubility product, although it's not really the same thing, because when we talk about a solubility product, we talk about relatively insoluble minerals, and we look to the extent to which they disassociate. So this has a certain dissociation, but it's not really a pure mineral. So it's analogous, but not the same thing. And again, that's why we use Kw instead of Ksp. So what about the value of K sub W? Well, it is about 1.0116 times 10 to the minus 14. And what is this equal to? Again, it's equal to the concentration of hydrogen and the concentration of hydroxyl when multiplied by one another. But as we indicated earlier, if the concentration of hydrogen is equal to the concentration of hydroxyl ion, so if these two things are equal to one another, we can make a simple substitution. This is simply going to be equal to the hydrogen ion concentration squared. And so if this whole thing is equal to that, then the concentration of hydrogen ion itself would simply be the square root of all this here. And so if we take the square root of 1.0116 times 10 to the minus 14, then we would get 1.0058 times 10 to the minus 7. And now, remember before we had something called PKSP, where we took the minus log of KSP. Well, we could play the same kind of trick here. We can have something called pH, which is equal to minus the log of the hydrogen ion concentration. And if we take the negative log of this thing here, then we would get 6.997, which is something we can round off to being about 7.0. And so that's how we derive the pH of neutral water. So the pH of pure water, nothing else added to it, would be 7.0 at, by the way, 25 degrees centigrade. That's where we derive this value here. So the Kw, 1.016 times 10 to the minus 14. It's not at any temperature, not at an arbitrary temperature, but at so-called room temperature, 25 degrees centigrade. So if we have pure water, nothing else added to it, the pH should be 7.0. So that's how we derive pH. Increase the hydrogen content. Since we have the minus log, it's a little bit tricky here, but you could try it. Try increasing the hydrogen content, make that a little bit larger, and the pH will go down because of that minus log part. And then if we increase the OH by contrast, then the pH would go up. So that's our definition of pH. That's where it comes from.